For your next lecture, you should have the basic chemistry notes in front of you. And I know what you're thinking, Ms. Sager, this is biology class. Why in the world are we learning about chemistry? Well, the answer is because chemistry is a really cool science in that it has so much to do with other types of science. So even though this is biology and we are talking about living things involve a lot of chemistry, and we will be covering a lot of topics that involve chemistry this year. And so it's important that you have this foundational knowledge of chemistry. So we are going to start our notes at the building blocks of life, and we're going to zoom in right here to the atom. So this is just basic knowledge. Hopefully you've at least heard the word atom. And the atom, like I said, is the building block of all matter. All matter. Everything that you can think of. The table that you're sitting at, the pencil or pen that you're writing with, you yourself, you're all made of atoms, either living and non-living. So anything on Earth, because you're either living or non-living, is made of atoms. It's pretty crazy when you think about it. So an atom, its definition, is the smallest particle of an element. And an element is just a pure substance. You've heard of elements before, and we'll talk about plenty in this class. But an element is just a pure substance, one thing. And that element is made up of an atom. And it's the smallest particle of an element that retains properties of that element. The important thing about an atom is that it cannot be broken down. An atom is an atom. It cannot get any smaller. We'll skip down to this bullet right here and then go back up here. But right now on this fourth bullet, it says atoms consist of protons, which are abbreviated with a P and a plus sign. Why do they have that plus sign? That plus sign, or this sign right here, indicates their charge. So protons are positively charged. Same goes for neutrons. A lot of people think that neutrons, like protons, is positive because it starts with a P, and neutrons is negative because it starts with an M. No, that's wrong. That would be easy to remember, but it's not that way. Neutrons, think of neutral, and if something's neutral, it doesn't really take a side, have a charge, and that is neutral. Neutrons don't have any charge, and we indicate it with this, what looks like a degree sign. And then the third things that atoms are made up of are electrons. And electrons, as you can see here, are the negative particle. So while the atom cannot be broken down, it is still made up of things. It just can't be taken apart. Those protons, neutrons, electrons will always be part of that specific atom. And going back up to the third bullet, there are 6 elements that make up 98% of the human body, of an organism's body. So an organism that could be any living thing, really. It doesn't have to be just humans. It could be any type of animal, plants, things like that. But these 6 elements right here, it makes this nice acronym called CHONSP, which I won't ever say because that's a hard word to say because it's not a word. And I'll write it over here. The C is the element carbon. So if you don't know this or think you might forget it, I'd recommend writing this over here, because these are typical elements that you will need to know. The capital H stands for hydrogen. The O is very important, oxygen. The N is nitrogen. The P, that's a tricky one. It's phosphorus. Oh, I might have spelled that wrong. I don't know. And then the S is sulfur. So these 6 elements right here make up 98% of what we're made of. The other 2% that we're made of is just trace elements that are in really small quantities. And out of these 6, oxygen is the most abundant in our bodies. And a lot of people like to say, oh, well, the human body is made 70-60% of water. Well, if you think about it, what's water made of? Water is H2O. So these two elements are very abundant in the body. However, carbon comes in second place, and we'll be looking at why. But speaking of water, we will move on over here where it says water, the universal solvent. So a solvent is anything that is able to dissolve other substances. And sometimes when we talk about solvents and things dissolving other things, people automatically assume acids because acids are crazy and they dissolve things. But water, if you think about it, can dissolve a ton of things. So how do you make sweet tea? You make tea, which is primarily water, and you add sugar to it. And does the sugar stay in the sugar crystals? No, it gets dissolved into smaller pieces, so you have that nice, tasty drink. Same thing for Kool-Aid. Kool-Aid would be, in this case, the Kool-Aid powder would be the solute, because it is being dissolved in the solvent, which is water. So let's move on to solute, because it's easier to talk about them together. A solute is just anything that is dissolved in the solvent. So in the case of, let's say, salt water, which is something we are familiar with, what is going to be the solvent? The water is. When you have water, it's a good guess that it's going to be the solvent. And that would make salt the solute, because it's being dissolved in the water. And water has another property that is very important in biology, and it is a polar molecule. It's a polar molecule, meaning it has a charge. It has a charge because hydrogen has a slightly positive charge, and oxygen has a slightly negative charge. And do these just cancel out in water? No, because in water we know it's H2O, meaning it has two H's and only one oxygen. So water has an overall positive charge because it has more hydrogens, which are positive. And this is a very important thing to remember, that water is a polar molecule. And the way I remember that, and I've taught other people how to remember it, is that polar, obviously you think of polar bears, and where do polar bears live? In the ice or the water. So water is a polar molecule because polar bears like water. So hopefully that helps you. Now that we've gone over that water is the universal solvent and that water is also a polar molecule, we'll talk about some other examples of things dissolving things. So in chemistry, there's a saying that like dissolves like, meaning things that are similar will dissolve in each other. For example, polar substances will dissolve polar substances, and nonpolar substances dissolve nonpolar. Makes sense. Polar dissolves polar, nonpolar dissolves nonpolar. So in the case of up here, where we were talking about salt water, since you know that water is a polar molecule and salt dissolves in water, you can assume that salt is a polar or nonpolar. Which one? Salt is a polar molecule, meaning that it also has a charge, and that's why it dissolves in water. Okay, moving on to this second bullet right here, we're going to talk about organic compounds. Now, organic is a word that you've probably heard, but I'm going to crash everything you know about it because the way that you probably have heard about it is not the way that we use it in science. So organic compounds, like it says here, those are different. It's a different use of the word than you're familiar with. So when you hear the word organic, you might think of like natural or it's healthy food and things like that. If you have organic peas, I don't know, then they're healthy and natural and don't use any pesticides. That is not what we're talking about in science, okay? Organic compounds are molecules that contain carbon. They contain a backbone of carbon and have hydrogen atoms. But the thing here, organic equals carbon. I want you to write that somewhere up here because it's super important to me that you know the difference, that organic equals carbon. If we're talking about an organic substance, all we're saying is that it has carbon in it. And I'll draw a backbone of carbon in a minute. So just hang on for that. It doesn't mean that it's just has to have carbon. It will have hydrogen because of the way that carbon likes to bond. And it might have some other atoms also. It might have oxygen, things like that, nitrogen. But it just means, organic means that it has a backbone of carbon. And remember when I said that carbon is the most abundant organism found in humans and in most organisms is because of these carbon backbones. However, though, we know so much about them, about organic compounds, that we can also make them. So they're not just found in nature, we can make them synthetically. Synthetic just means basically fake, man-made, and they can go into things like medicines. Moving on to the third bullet here, if we talk about organic, then obviously there has to be an opposite. So inorganic compounds do not contain a carbon backbone. So this could be many different molecular compounds and all ionic compounds. So anything that's an ion is not going to have carbon in it. So this one, carbon dioxide, you might be familiar with. Carbon dioxide right here. It obviously does have carbon in it, but it's not a backbone. It doesn't have a chain of carbons in it. And then there's oxygen gas, or O2, and H2O, and NaCl, which is table salt, and nitrogen gas. So the same thing goes if people think organic means it's healthy, it's natural, it's good, then people often think if it's inorganic, that means it's bad for you and it's not healthy. But one of the main things that humans need to live, water, is an inorganic compound. So it's not a bad thing. It's just doesn't have a carbon backbone. And to reiterate that point, down here, organic does not mean good or healthy. And in the same page, or inorganic does not mean bad or unhealthy. And down here I have a little room, so I'm going to draw a backbone of carbon. And this is just an example of what a backbone is. It means that it has a lot of carbons. It'll literally be a chain like this. It could be dozens and dozens of carbons long. Let's say there's an oxygen right here. And then on each of these carbons, there's going to be hydrogens, because carbon likes to make 4 bonds. So there's literally going to be hydrogens all down this chain. You get the gist of it. These are all hydrogens, hydrogens, hydrogens. There would be another hydrogen right there. Okay, so when it talks about a backbone of carbon and hydrogen, the hydrogen's only there because it's one of the main things that can bond with the carbons. We are going to go ahead and move over to this side of the notes, chemical bonding. So you've probably heard of chemical bonds. I know I've mentioned it on this page already. But chemical bonds are basically just attraction between atoms that allows them to become stable. And it forms chemical compounds. And lucky for us, we've already drawn this chemical compound over here. And so, like I said, carbon here likes to form 4 bonds. That's what makes it stable. That's what makes it happy. So here you can see it has one bond with this other carbon right here. It has one bond with this carbon right here, and it has one with each of these hydrogens. So carbon has 4 of these bonds to be happy, and there's many different examples of chemical compounds that bond together. And there are different types of bonds. One of the first bonds that we'll talk about is an ionic bond, and it results from the transfer of electrons. That's what this symbol is for, remember? It means electrons, which are the negatively charged particle found in the atom. But ionic bonds results from the transfer of electrons and the attraction between resulting oppositely charged ions. So in this case, we've heard the saying opposites attract, and the same is true here. It'll have a positive and a negative bonding together because they're oppositely charged and they're attracted to that. The next type of bond that we're talking about is covalent bonds, and they result from the sharing of electrons. So up here on ionic bonds, it's a transfer of electrons. So one element will lose their electrons, the other one will completely gain them. But here on covalent bonds, they're just sharing them. They're both connected to those electrons, but the original one still has them. And then the third one are hydrogen bonds. They are very common and also very weak. Anything with a hydrogen bond is going to be easy to break apart. Okay, and with chemical bonding, we can also talk about chemical formulas. Chemical formulas are special because they show the type and number of atoms in a molecule. So looking right here at the first bullet, H2O, hopefully we know that that's water, and it has 2 hydrogens and 1 oxygen, so 2 plus 1 equals 3 atoms. Here we have C6H12O6, which we might not be as familiar with. That is glucose, which is a very important sugar that we will talk about plenty. You will be so familiar with glucose. But it has 6 carbons, 12 hydrogens, and 6 oxygens. So it has 24 atoms. And then there are also structural formulas that show the type, number, and arrangement. Type, number, and arrangement of atoms. So the structural formula are written right here, drawn actually. So the structural formula for H2O, there's going to be the O in the middle, and and coming at a little diagonal is each hydrogen. Okay, so you should be drawing that. And then it can be even more complicated, and you could have a hydrogen here, one here, 3, 4, and then you have 2 carbons, and 2 oxygens. And remember how I said that carbon likes to form 4 bonds? Let's go ahead and check. There's 1 bond, there's 2 bond, 3, 4, so carbon is happy and stable. Let's erase those. And let's look at this carbon over here, the one on the right. It has 1. It has 1, 2, and then right here is a double bond, so there's 1 and 2. So carbon's happy, carbon's stable, and it is in a perfect structure. And now we're going to move back over here, and we're going to talk about chemical reactions. Chemical reactions are the process of forming or breaking chemical bonds. The reactants, it's the chemical reaction, the way we write it is made up of different parts, and we're going to talk about those. So the reactants are written on the left of the arrow, and the products are written on the right. So in this example, these right here would be the reactants. I'll just draw an arrow. And the products are going to be these. You should also be writing this formula right here, which is one that I am sure you have seen before. So go ahead and write it, and then I'll talk about it. So chemical reactions or formulas are always read left to right, and you read it. This would be CO2 plus H2O, and then this arrow we say yields, meaning it makes it basically. So CO2 plus H2O yields C6H12O6, which I said was glucose, and O2, which is oxygen gas. And do you know what reaction this is for? What biological process? Let's break it down. So what that you're familiar with takes in CO2, carbon dioxide, which is in the air, and takes in water and makes sugar and oxygen. This process is known as photosynthesis. So go ahead and write that, just so you know that that's photosynthesis for the future. Continuing on with some basic chemistry, I always like talking about the pH scale, which again, like a lot of the basic concepts that we're going to talk about in chemistry, you've probably heard about, but we're still going over it, so I know that you know. Okay, so pH scale is a scale to measure the acidity or basicity of something. So whether it's an acid or a base. The scale goes 0 to 14. So what's halfway between 0 and 14? 7. A pH of 7 is known to be neutral. It's not an acid or a base. It's neither. It's neutral. An example of this would be pure water. And that word pure is very important because if I just go and get tap water, it's probably not going to have a pH of 7. Chances are it'll be a little bit more acidic. Tap water is normally more acidic, so whenever you're performing an experiment, you should never use tap water because the experiment is probably assuming that you're using pure water that is neutral. And pure water could just be distilled water or filtered water, things like that. It just doesn't come out of the tap. So acids that we talked about, those are compounds, and this is very technical. They're compounds that release hydrogen ions upon dissolving in water. Earlier we talked about the charge for hydrogen. It's worth mentioning here. What is the charge for it? It's positive, and since hydrogen's symbol is H, lots of times if we're talking about hydrogen ions, we can just put H plus, and we all know what we mean. And then upon dissolving in water, remember that water is a solvent, and things dissolve in it. Examples of acid are hydrochloric acid and sulfuric acid. There are plenty of others, but those are two very common acids if you're talking about acids. And acids have a pH of less than 7. So basically a pH of 1 to 6. The lower it is on the scale, the more acidic it is. And then we know 7 is neutral. So we'll move on to bases. Bases are compounds that release hydroxide ions upon dissolving in water. Hydroxide ions can be abbreviated OH negative. They are a negatively charged ion. An example of a base is NaOH. Which is just sodium hydroxide. And we'll talk about over here all the examples of things that you're familiar with. And bases have a pH of greater than 7, meaning 8 to 14. Before we move on to the scale, I want to go down here to this fun little blurb here. And it says, I wanted to add this in here because you may know of the dangers surrounding acids. You might have heard of acids a lot more. Acids are scary, like people get acid thrown in their face and it, can cause chemical burns and things like that. And so people assume, if acids are bad, that means that bases are good since they're at the other end of the scale. And that's what people kind of assume a lot. And that's not quite the case. Strong bases can cause the same side effects of strong acids. Strong bases, which is on the other end of the scale, that would be like a pH of 13 or 14. Strong bases can cause the same side effects like skin melting and irritation that acids can. So, safety precautions must be taken at all times, even if you're just working with, oh, it's just a base. It could still melt your fingertips off. So keep that in mind. Now we'll go over here to this pH scale that has some common solutions that you're familiar with. So starting off, we have the pH of 1 right here, and so this is less than 1. So battery acid. Battery acid is very acidic. It has acid in the name. It's very acidic. And then in between 1 and 2, so around a 1.5, is your stomach acid. So the acid that just lives in your stomach and helps digest things and break down things. It's very, very acidic. So that's why if you get sick and you throw up, your throat might really be sore because you've been throwing up your gastric or your stomach acid, and so it's causing irritation to your throat. And then coming in at about a 2.4 on the pH scale is lemon juice. Lemon or any type of citrus is going to be pretty acidic. Coming in at a 2.5 on the pH scale is cola, any type of soda, carbonated beverage of your preference. And so, this is a side note, a little rant on my part. You've probably seen, I don't know if you've seen it, but there's this video going around on Facebook, as things do. It was going around on Facebook and it was showing someone pouring Coca-Cola on their car engine to clean it. And they were like, and this is what you're putting in your bodies. Well, while it should be drank in moderation, let's look, because cola has a pH of 2.5. And where does the Coca-Cola go when you swallow it? It goes into your stomach, which has a pH of 1.5, which means your stomach acid is way more acidic than the things you are putting into it. So keep that in mind next time someone blames you for drinking a lot of cola. Say my stomach acid can handle it. Moving on to a pH of about 2.8, vinegar. So just to remind you, as we're going down this way, or as we're increasing in number, it is getting less acidic. The most acidic thing is going to be up here. So at a pH of about 3.5, we have another citric acid, orange juice. Good old OJ is still pretty acidic. At a pH of 5 is coffee. At about a 6.4, you don't think of milk being acidic, but milk is slightly acidic since it's just below 7. And here we go. Here is pure water. Pure water is supposed to have a pH of 7. Lots of times it's more in this range over here, depending on where you get your water from. At about a 7.3 or 4 is blood. So blood is very near neutral, but it is slightly more basic. Another very basic compound at 9.5 is hand soap. And obviously, hand soap isn't harmful. We use it every day on our skin, so it doesn't cause any irritation. But down in this area is where we might start getting irritated if we get things on us. So, ammonia is the first strong base that we'll talk about. And then at a 12.5, there's bleach. So bleach is a pretty strong base. It's not that safe of a compound. It's a base, so it could still cause irritation to your skin if you get it directly on your skin and it's not diluted with watered down at all. And then one of the most basic compounds you could have is lye or detergent. Back in the olden days, they used lye to make types of body soap, but they don't anymore because it's very basic and it could cause some irritation if you have sensitive skin. Okay, so that sums up our pH scale for our notes. We're going to look at the big idea that I wanted you to get from these notes. So, like I said, while this is biology, we must understand the things that we cannot see. So one of the main things I love about biology is that we can see it, we can observe it. It's a lot easier to understand because we can see it and we can observe it. But chemistry is not the same way. It's things we cannot see. But in order to understand biology, we have to understand chemistry. So we must understand the things we cannot see, which is chemistry, to understand the things we do see or observe in biology.